Hello, Math 256 friends. Hope everyone is doing well. Welcome to 11.4, section on comparison tests. Remember, we are looking at sequences and series. In chapter 11, our goal is to determine whether or not a series converges or diverges. Don't forget the previous tests that we've discussed. If those aren't working, then we've got some new tests for you today. Today, we're going to talk about comparison tests. The first one is just simply called the comparison test. So later I'll abbreviate it with just CT. So the comparison test says, suppose we have two series, and if I don't put this, it's understood. Just go from 1 to infinity. Our series with positive terms. Now remember, these tests are dependent on their hypotheses. So in this case, we have to have a series. We have to have series that contain, actually, I should say, all non-negative terms, and the nth term in the sequence A is always less than the nth term in the sequence B. So A falls completely between 0 and each term in the sequence B. And if this is the case, then if we know something about B, we can determine something about the series A. And if we know something about the series A, we can determine what's going on with B. So again, we have to remember that all the terms of A are sandwiched between 0 and the series terms of B. If the series B converges. Oops.
One moment.
Nope, I don't need you, Siri. If the series B converges, then if these conditions are true and hold, the series A also converges.
Sorry, I couldn't quite hear you. Could you please repeat what you said?
All right, let's see. Let's turn that off and put this over here, and hopefully it will leave me alone. All right, so what this is saying is that if we can sandwich a series, the terms of a series between a convergent series and 0, then that series must also converge. So if it's below a convergent series, then that one must also converge. Okay, if we know something about this, we can determine something about this guy. So if we know something about the series AN, in particular, if the lower or the smaller of the two series diverges, in the terms of the series BN fall above the divergent series, so if this is above a divergent series, then it must also diverge. So again, it's kind of common sense. If we can bound a series above by a convergent series, then that also must converge. If we can show that a series falls above a divergent series, then that one must also diverge. That is the comparison test. So let's look at an example. Is the series 1 over 2 to the n plus 5 convergent or divergent? Now we have to be careful here because this is sort of a geometric series. The problem is this plus 5. So we can't call this a geometric series. If we didn't have the plus 5 here, we would know that this is a geometric series with common ratio 1/2. So our instinct is that this is going to behave like the geometric series, 1 over 2 to the n, but this plus 5 doesn't allow us to call it a geometric series, so we need some other method. So I'm keeping in mind that I'm thinking this is going to behave like 1 over 2 to the n. Now let's notice here, isn't it true that 2 to the n plus 5 is always greater than 2 to the n? Because if we take anything and add a positive value to it, it's going to be greater than the value itself. So therefore, based on properties of algebra, the reciprocal 1 over 2 to the n plus 5 is less than 1 over 2 to the n, because we have this property. If A is greater than B, then 1 over A is less than 1 over B. Right, so that's what I just used in algebra. All right, so I can see that the terms of this series are bounded above by the geometric series 1 over 2 to the n. And I know this converges, so this must also converge. But we have to show all this. So first of all, again, in the hypotheses, We just showed that the terms of this series, I'll call this AN, right? And I'm going to call this guy BN. So I just showed that AN is less than or equal to BN for all n. I just have to confirm that the terms of the series are positive, and 2 to the n plus 5 is greater than 0 for all n. Right? So the terms are positive. So now let's look at this series, 1 over 2 to the n. Well, let's just get it into the form of a geometric series. So 1 over 2 to the n is equivalent to 1 over 2 to the n, which is equivalent to 1/2 times 1/2 to the n minus 1. Now it's in the necessary form to call it a geometric series. So this is geometric. A equals 1/2, R equals 1/2, and we know this converges because of this. 1 over 2 to the n converges. So therefore, we bounded this series above by a convergent series. So we can conclude. So therefore, 1 over 2 to the n plus 5 must also converge, because we bounded it above by a convergent series. Right, now we have to be super careful here. Let's suppose I just simply change the sign of one thing in this series. What if I change this? Well, again, we expect it to behave like 1 over 2 to the n, and it actually does, but we need to show this using calculus. Problem is, let's see, we have to show that this is, we know it behaves, we expect it to behave like 1 over 2 to the n, right, which converges. Right, so need to show 1 over 2 to the n minus 5 is less than or equal to 1 over 2 to the n for all n. Upside down A means for all. So is this true? Well, let's see. N equals 1, n equals 1. We get 1 over negative 3, less than or equal to 1/2. That works. N equals 2. 1 over negative 1, less than or equal to 1 over 4. That works. N equals 3. Yeah, it seems to work, right? But how can we do it in general? Like it seems it, but we can't, and we'd have to show this for every n. So this would be 1 over 8, would be 3. Oh, wait, hold on. Oh, 3, 2 times 2, 1/8. Not true. So this, in fact, isn't true starting at 3. So this series is not bounded below. This series is not bounded below by this series. It's not true. So be really careful with the signs here. Algebraically, 2 to the n minus 5 is less than 2 to the n. So if I looked at the reciprocal, right? And that, when we're trying to use the comparison test, we know that this guy converges, right? We know that that converges, But if we have a series that's greater than a convergent series, we have no idea how this behaves. In order to determine how this behaves when we compare it to a convergent series, it has to be less than. So here, the comparison test cannot be used. So the comparison test can't be used, and we need another type of test. So be careful. You have to make sure when you're comparing a series to another series, if you're comparing it to a convergent series, it has to be less than the convergent series in order to conclude it converges. If we knew that this diverged, then we could conclude this diverged, but this doesn't diverge, so that doesn't help us. So, And yes, we have another test. The next test is called the limit comparison test. So I'll probably abbreviate this later. LCT, the limit comparison test. So the limit comparison test can be used when the comparison test fails. The limit comparison test says that if we have two series all with non-negative terms, then usually one of them we need to know how it behaves. If we take all the terms of the series in AN, compare it to all the terms of the series in BN, take that ratio, calculate it, and if it equals some constant, as long as this constant is not 0 and it's a positive number, then either both converge or both diverge. AN and the series BN either both converge or both diverge. So what we typically do is we let BN be a series that we know how it behaves, and then we compare it to AN. So let's revisit this guy. Let's revisit this. We expect this to behave like 1 over 2 to the n, which we know converges. So let's use the limit comparison test with 1 over 2 to the n. So we're going to let this be the one we're looking to see how it behaves. I always let B be the one I know how it behaves. And we're going to calculate the limit as n goes to infinity of 1 over 2 to the n minus 5 all over 1 over 2 to the n. And we just do our algebra here and clean this up. We don't like fractions and fractions. So dividing by a fraction is the same as multiplying by its reciprocal. All right, so this limit gives me, when I plug in infinity, I get infinity over infinity. So L'Hopital's rule kicks in here. And I can use L'Hopital's rule to calculate this limit. This says if I have something of the form 0 over 0 or infinity over infinity, I can take the derivative of the top, which would be the natural log of 2 times 2 to the n, all over the natural log of 2 times 2 to the n minus 0, which is, the limit as n goes to infinity. Well, the natural log of 2 over 2 to the n over the natural log of 2 over 2 to the n is just 1. So this limit is just 1. So by the limit comparison test, since 1 over 2 to the n converges, and this limit of 1 over 2 to the n minus 5 over 1 2 to the n equals 1, we can conclude that 1 over 2 to the n minus 5 also converges. There we go. Limit comparison test. All right, so notice I said limit comparison test and I said 1. And there's 2 more parts to it. And interestingly, I think your book only includes this one part, but there are 2 other conclusions. That you can find in different texts or possibly even online. The limit comparison test, there's another criteria. It says additions. So there's more conclusions we can make if this limit, as n goes to infinity, of an over bn is equal to 0. Here, we can make the conclusion that they behave the same if the limit is positive, but if the limit equals 0 and the one we know converges, then the one we're looking at must also converge. Okay, now be careful. If this limit equals 0 and bn diverges, we can't make any conclusions. So if the limit equals 0 and the denominator one converges, the denominator series converges, then we can conclude the numerator series converges. And lastly, if the limit as n goes to infinity of an over bn, whoops, I wrote off my paper, equals infinity, and the denominator series diverges, then the numerator series also diverges. So again, be careful here, because if this limit equals infinity and the denominator series converges, we can't make any conclusion about the numerator series. All right, so let's do a couple of examples. What do I have here for examples? Let's look at this comes with lots of practice, and I so wish I was in class with you guys to go over this. I'm going to do 1 over the square root of n squared minus 5. All right, now here, n can't be 1. We can't start at 1, because if we started at 1, we're going to be entering the world of imaginary numbers, and we don't do that. N can't be 2, because we'd still be taking the square root of a negative number. So I'm going to start this series with 3. A finite number of terms eliminated or added to a series does not affect the convergence or divergence. So converge or diverge. All right, so the tricky part here is deciding what are we going to compare this to. So things to keep in mind. I'm thinking this is going to behave like 1 over n. And how do I know that? Well, as n gets infinitely large, this 5 becomes irrelevant. So like if n was 1,000,000 and we did 1 over the square root of 1,000,000 squared minus 5, this is such a small contribution eventually that it doesn't contribute to the ending behavior of the series, or it does so little that we don't even consider it. So what I see here is that this is going to behave like the leading terms, or 1 over the square root of n squared, which is 1 over n. So I'm thinking that this is probably going to behave like the series 1 over n. Now the series 1 over n diverges. This is the harmonic series, and we've shown several times that this diverges. So the only way it would be useful to compare this guy to this guy is to show that this one is greater than this one. In order to show something about a series compared to a divergent series, would have to show that it was greater than. If this is less than a divergent series, then that's not going to be helpful, because if it's smaller than a divergent series, we don't know if it converges or diverges. So let's look at some algebra here. Isn't it true that n squared minus 5 is less than n squared? Because if we take anything and subtract 5, of course, it's less than its original self. So therefore, the square root of n squared minus 5 must be less than the square root of n squared. And here, n is greater than or equal to 3, right, which will become important. So 1 over the square root of n squared minus 5 must be greater than 1 over the square root of n squared. But the square root of n squared is just n. So I just showed algebraically that 1 over n squared minus 5 is greater than 1 over n. which we like, because when a series is, the terms of a series are greater than the terms of a divergent series, then we know that this must diverge. So, since n squared minus 5 is greater than 1 over n for n greater than or equal to 3, and you can always assume, we don't have to reinvent the wheel here, the harmonic series always diverges. Therefore, 1 over the square root of n squared minus 5 also diverges. Here we go. All right, let's try one more example I'll say by the comparison test. I'll throw one more out there. I'll let you guys pick away at these and then zoom in with questions. I'm waiting to do some Math 256 problem solving. 4n plus n converge or diverge. All right, let's see. So my gut is to think, I don't know, as n gets really big, this is going to contribute to it, but 4 to the n, like 4 to the millionth power is going to be really huge. So my gut is, does it behave like the geometric series 1 over 4 to the n? We know that this is geometric. We can rearrange it and get r to be 1/4, and so this converges. So therefore, we have to somehow compare this to this. So can we show that this is true? Can we show that 1 over 4n plus n is less than 1 over 4 to the n for all n? Well, clearly this is true, since 4 to the n is greater than 0, and n is greater than 0 for n greater than or equal to 1. So now we just have to show this relationship right here. Can I show this? No. 4 to the n plus a positive number. Now remember, n is greater than or equal to 1, so 4 to the n plus something positive is always going to be greater than what we started with. So therefore, 1 over 4 to the n plus n is less than 1 over 4 to the n. So therefore, by the comparison test, 1 over 4 to the n plus n converges, since it's bounded above by a convergent series and all the terms are positive. All right, so the best way to get good at this is to pop out these on your own. So what I want you to do is read 11.4 in Stewart, exercises, can never do enough, 3 to 31, odd, every other odd, do all of them, whatever works for you. I believe this is, let's see, X, Y, Z, 5.4 problems. And there you go. All right, up next is, I'm not even sure what's up to, oh yeah, the ratio and the root test. Okay, see you guys soon. Hope everybody's well.